Well, Ron Klemencic, welcome and thanks for joining us.
Appreciate that.
So it seems like an appropriate time to ask, now that you're getting the Fazlur R Lifetime Achievement Award. What do you think was the most technically challenging project you've worked on in your career?
That's a fascinating question because all the projects I work on have some challenge. And to pick out the one that's the most challenging is proving to be quite difficult. I'd offer this, that lifetime achievement is a bit daunting to me because I'm only 53 and I still got a long ways to go. So we'll call this more of a progress report than a lifetime achievement. Probably the thing that has been one of the hallmarks of my career to date has been the development of performance-based seismic design of tall buildings. And basically what we did starting in about the mid-90s was turn the design methodology on its head and really developed a whole new approach to designing tall buildings, in part because we had the tools available to us, analytical tools, technological advancements in seismic design and what have you that we could employ that weren't available to our forefathers. And so using kind of that the new resources, the new tools, the new computer software that we had available to us to kind of take a more sophisticated, more direct approach to seismic design was kind of what prompted all of that. What we discovered in moving forward with that methodology was a lot of resistance. And so that's proved to be maybe the most challenging aspect of anything I've ever taken on.
What do you mean by that methodology?
Well, so we are able to now explicitly model the performance of the building subject to any number of earthquakes. Before, we'd estimate it. We'd do hand calculations, we'd do some thoughtful guessing, we'd design and we'd hope. Now we can actually very quantitatively, very rigorously calculate with a seismic ground motion input. It's like you see on the evening news, the seismograph record. We can actually digitize that, make that the input to the computer model the building's parts and pieces explicitly, shake the building in the computer and see how it performs. And we do this 20 or 30 or 40 times with any given building with different earthquake records. And so it allows us to get a lot more efficient with the design and a lot more directed. Rather than kind of guessing where to put the material and hoping that it works, we actually now can quantifiably say, yes, it needs to go here and we don't need so much there. So we have safer buildings, more reliable buildings, and more cost-effective buildings.
But when you look back on your career and all the projects that you've done, there aren't any that stand out as really breakthrough moments of technical challenges that you overcame?
So maybe there's three that jump in my head. The first one is a project in San Francisco called the Infinity. It's two 40-story condominium towers, and in and of themselves not particularly notable. They're nice-looking buildings, but not particularly tall or particularly anything. They were the first performance-based seismic design towers we did in California. And they were subject to incredible scrutiny by the California establishment, so to speak, the engineering establishment. It took us 2.5 years to get those buildings, the design of the buildings approved because of all the rigor we had to go through to demonstrate our design. Then fast forward to just recently, the Salesforce Tower, also in San Francisco. It's the tallest commercial office building on the West Coast. And it's kind of set a new high water mark for performance-based seismic design. So those two are technically challenging. I'd say, interestingly, as a tall buildings guy, which is what I do, my favorite project is actually not even a building. It's a 1-story tall picnic shelter in Lincoln Park Zoo here in Chicago. It's a piece of architecture that I worked on with Jeannie Gang. It's an open air picnic shelter. It's maybe 2,000 square feet. It's tiny, but it's a piece of art and it's beautiful.
I've been there. It is beautiful, but
Yeah.
why is it your favorite?
The process that we went through to design that building, it was this incredible process of collaboration and discovery and research and invention. And so you've been there, you've seen it's made of wood, and the wood is bent in 3 dimensions. First time that I'm aware of, at least in a building structure, that wood has been built, actually bent in 3 directions to create the structure. And we had to figure out how to do that. So we ended up working with shipbuilders and with furniture makers and all sorts of interesting and unique people outside of the building industry to help us understand the material, how we could fabricate the material. We tested it, how we actually built the building. And it was an incredible journey. And so it's quite ironic that the tall building guy like me, my favorite project of all time is a 1-story picnic shelter.
Yeah. Well, back to tall buildings. When it comes to seismic performance-based design, like you were talking about earlier, what are some of the things that you discovered through that process that we now know about how to design buildings so that they can withstand seismic activity that you couldn't know before?
Yeah, not surprising, but very clearly what we've discovered is that when tall buildings respond to ground shaking, that they don't respond in the way our building codes believe they respond, meaning the building code thinks that the tower stands there and the ground shakes and it sways back and forth as the ground shakes. And that's not how it reacts. It actually, I've used the analogy over the years, a tall building is like a teenager, meaning my teenage kids, they when they're sleeping, it's really hard to wake them up, right? And you got to shake them and you shake them and you shake them, and they're really groggy. And then eventually they finally kind of spring to life. This is how a tall building responds to ground motion. You can shake it and shake it and shake it, and it doesn't really wake up right away. So its initial response is very, what's the right word I'm looking for here? It doesn't react immediately, and then when it does react, it doesn't necessarily sway like this back and forth. It actually kinks. And the highest stresses in the building tend to be about halfway up. So because this bend in the building that happens, it's almost like whiplash. If you had like a buggy whip and you crack the buggy whip, it's that kind of curved shape that the tower takes. And so the highest demands, the highest earthquake stresses in the building tend to be about half to 2/3 of the way up the building, not at the base. And so this causes us to rethink how we allocate the strength of the building. In fact, we've designed many buildings now where there's more rebar and more concrete and more steel halfway up the building than there is at its base, because that's where the demand is. And we only discovered that through this more rigorous computational approach to design. Whereas before, historically, everybody thought, well, of course, the biggest forces are at the base, you know, the tower swaying back and forth. And this is true of wind design, but not true of earthquake design.
One more thing I want to ask you about seismicity, just briefly, is since you've worked so much in San Francisco, and there's been a lot of talk lately about, you know, when's the next big one going to happen? When's the next big earthquake going to hit San Francisco or the Pacific Northwest? There's certainly been a lot of seismic activity in Italy and even in Oklahoma, where it usually previously had never happened. I just wonder if you think that there's a new sense of understanding about seismic. I mean, are we ready? Are codes and is the profession taking this issue seriously enough? Are we prepared, or could we be in for a bad situation?
Yeah, well, are we prepared? No. Are we making strides forward? Yes. Certainly the performance-based design of high-rise buildings is a big step forward for high-rise buildings. But when you look at the inventory of all buildings, high-rise is just a small fraction of all buildings. And then there's infrastructure, and that's probably the more critical part: roads, bridges, water supply, gas supply, electrical power grid, etc. And those infrastructure pieces are kind of woefully behind in upgrading to perform in these major earthquakes. And so the concern going forward isn't so much with the building stock, at least first. It's improving the infrastructure. In California, they're spending quite a bit of money improving the water pipelines and whatnot for seismic activity, but there needs to be a lot more work and a lot more money, unfortunately, spent in that area to have the infrastructure in place to serve the buildings. It's one thing to design a building to survive the earthquake, but if you can't have water or electricity or plumbing work, what's the point? So there's a lot of effort going on there, but it's going to be decades before that's solved. So,
one more question I have: earthquake or not, a lot of tall buildings, you know, can reach the end of their life, and we've seen the tallest building ever demolished, the Singer Building in New York, at 187 meters. Obviously, that's potentially wasteful. You'd like to see a building last as long as it possibly could. There's probably things at play beyond just architecture and engineering here. But how should we design buildings so that they're resilient, that they last, they have a long, fruitful life, and we're not demolishing them?
Interesting question. There's a lot of aspects to this. In fact, we were just talking about this topic at the CTBUH conference in Shenzhen. And the comment was made that, sure, today we're tearing down 20, 30, maybe even 40-story buildings to build 60, 70, 80-story buildings. Well, 50 years from now, maybe the new teardown mark is a 300-meter tall building, because we're building dozens and dozens and dozens of them all around the world, and we're going to start tearing down 300-meter tall buildings to build 600-meter tall buildings. The point of that discussion was that there's this kind of almost Neanderthal need in the human spirit to build. And as value of land increases and density still wants to increase, building denser and taller seems to just be the way that we're all wired. And so on the one hand, it's nice to think about building a 50-story building to be resilient and last for 1,000 years. And the reality is we probably don't need to. That we probably, at least the bones of the structure, the concrete, the steel, the structure itself will probably last, because those materials don't deteriorate generally. The guts of the building, the mechanical systems, electrical systems, et cetera, those will change in time as technology changes. And so in 20 years, 30 years, 50 years, these buildings now will need to be gutted anyways and call it adaptive reuse, right? New systems, new technology put in those buildings. We see that happen a lot in Chicago and New York, and that I think will continue, but just at higher heights. So we'll adapt some of the buildings and we'll tear some of them down, and that's just how we are.
Mm-hmm. Ron Klemencic, congratulations on receiving the Fazlur Khan Award, and thanks so much for joining us.
Thank you so much.